Hello.
I hope you're doing good. It's good to see you again. Let's go ahead and start talking about Chapter 13. We're going to be talking about hormones today. So, Monty's here. What do you think about the hormones?
I have no idea what they are.
Yeah, he has no idea. Anyway, so again, you saw that before. A couple things I wanted to mention that wasn't in my intro video. Remember, when it comes to college, be more proactive, less reactive. So if you're having difficulties with this course, please let me know. And I'll do my best to help you, because that's my job. That's my job as an instructor, is to help you. So also remember, please do read the book chapters. It helps. It really does. And the whole book is actually a really good book. I've read a couple different anatomy and physiologies, and I really like this one. So, yeah, and there's a couple places where it doesn't make a lot of sense, and don't worry, I've hit those places because I've read it too, and I will also, be going on occasion during these lectures going, hey, this didn't make a lot of sense in the book, so let me explain it in a way that, makes sense to me, and hopefully you two will go, oh, okay, that helps. So anyway, and make sure you're always hitting your deadlines, okay? That's why I have the checklist for you. It's to help you with the deadlines, so you're not sitting there at the last minute going, oh no. And if you do miss a deadline, I usually give you a gimme because at the beginning, but keep in mind, sometimes if you miss a deadline because you decided to go for a 2-week vacation, you might have to talk to me about that a little bit. So, just FYI, usually we can work something out pretty well. But anyway, just FYI, there are deadlines. Please try to stick to them. All right. We don't have a lab, so let's go ahead and jump into the endocrine system. So, endocrine means internal secretion. So, remember, endo means inside, exo means outside. So, the exocrine glands are like the sweat glands and all that fun stuff are not a part of the endocrine system. Endocrine glands only secrete inside of you. This is a major thing that helps maintain homeostasis in your body and works in conjunction with your nervous system. In fact, it took us a while to figure out what was nervous system and what was endocrine system, considering they're very, very much intertwined. I like to think of the endocrine system as like making phone calls. Because it's a long distance way, something that we can't always take the nervous pathways to say, hey, it's, when you hit puberty and a lot of these things get turned on big time, for sexual maturity. We don't use the nervous system to say, hey, it's time to grow hair in your armpits. So this is where the endocrine system comes in to kind of deliver those long-range messages to other parts of your body to let them know things need to be made, things need to start happening, XYZ, but without engaging your nervous system to do it, because that would be too many communication signals in too many different ways. So anyway, hormones are very powerful substances. It's a chemical messenger secreted by an endocrine gland into the bloodstream that affects the function of another cell or a target cell. Like I said, I kind of see it as like, making phone calls or texts to your friends and sit there and go, hey. Anyway, so, when I have to let my husband know that, something's come up and he has to go pick up Wesley from school, or in reverse, sometimes my husband has to drive a bus in the afternoon and he has to text me and goes, can you pick up Wesley? And then I go pick up Wesley. So that's kind of how I see hormones. General characteristics of hormones is they're needed in very small amounts. These guys are super potent, and they actually don't have a lot of, they break down very quick. They deteriorate very quickly. We call that half-life, and we're going to get into that in a little later. So we don't need them in large doses. Very small amounts, very potent. They also produce long-lasting effects in the cells they target. So that's why we don't need a lot, because they, can have major reaching effects down the line. A lot of them are regulated by negative feedback mechanisms. So if you remember from Anatomy and Physiology 1, Negative feedback mechanisms and positive feedback mechanisms are going to pop up all throughout the semester again. And negative is like when you go out of like a certain range and like, for instance, you get cold, what do? You put on a jacket. That's a negative feedback system. Or a positive feedback is something that it happens beforehand to move something out of a particular zone and then it moves back. So for instance, it's kind of like, predicting the weather, and then you sit there and go, I better bring an umbrella because I see dark clouds on the horizon. So that's kind of how I see negative feedback and positive feedback. It's like you get cold, you put on a jacket, or like, again, you get in your body, you get cold, you start opening up, or you start, making all the little hairs raise on your skin, so that way you can try to conserve heat, all sorts of different ways there. So negative feedback is when something goes out of the zone it's supposed to be in and we have to bring it back. Positive is when we actually kind of preemptively force it out. That's why we don't see a lot of positive feedbacks in the body. One of the major ones we're going to talk about at the end of this semester, which is pregnancy. Pregnancy is a huge positive feedback mechanism all over the place, especially labor. We'll get into that. But anyway, most things are negative feedback mechanisms, and hormones are definitely negative feedback mechanisms. So hormones may be a steroid, which is produced from cholesterol, which is fat soluble, lipids. They might be a non-steroid, which is water soluble, which are usually amino acid based. And there's a third type called steroid-like, because I've always found in teaching science and learning about science is that in biology, this is the reason we don't have like a lot of laws compared to, things like physics and chemistry, is because there's always yes, well, this is the thing, and then we have this weirdo in the corner. It's like yes, but, that's biology. It's always here's the rule of thumb we go by, but there's this one outlier. It's always that way. So yeah, we have steroids, non-steroids, and then the weirdos of the group, the steroid-like. Now, couple of things. So there's upregulation and downregulation. So upregulation increases in receptors. Now, keep in mind, receptors are basically how the cells kind of listen, or in this case, they kind of feel it, but they listen for the hormones. So therefore, if all of a sudden there's a decrease in these hormones, the cells will actually get more responsive. They'll actually put out more receptors in their membranes, so that way they can feel, for they can feel more for that specific hormone. They get more sensitive to it, in other words. I hope that makes sense. Then downregulation is, the receptors, they decrease the receptors because it's all of a sudden there's like a ton of hormones, and like the cells are like, okay, we get it. And so they try to become less sensitive to those hormones. It's kind of like listening to music. It's or like you're listening to something and you can't hear it very well in the other room, and you're kind of listening in, going, what are they saying? Whereas downregulation is somebody like blasting music in your ear and you're going, God, So that's the difference between upregulation and downregulation. So upregulation means they're like trying to listen up, and downregulation is like turn it down. So anyway, steroid and thyroid hormones, how we control DNA, basically. So what happens is the main steps of what happens is, remember, every cell in your body, of course, has a cell membrane, plasma membrane, and it happens to be made of phospholipids. Notice that there's these guys that are made of fat-soluble lipids. They dissolve in fat. Oh. So anyway, steroid hormone, for instance, he can actually pass through the cell membrane unhindered because the cell membrane is made of phospholipids. So he dissolves right through. It's like likes like. So they sit there and go, oh yeah, you're like us. Come on in, man. Come on in. And he's like, oh, thank you very much. I'm coming on in. And then inside, he will find a receptor protein and he will bind with it. then the receptor protein will then go, I must go tell the DNA to go make, or, to go through translation and transcription to make a new protein. And that's what he does. So he takes that and he goes in and he gets to the DNA and he says, we need to make a certain type of mRNA. We need this certain protein. We just got an order from above, which is usually your hypothalamus. We'll get to him in a minute. And then what happens is it goes through transcription, makes some mRNA, and then it goes out, finds a whole bunch of ribosomes. It goes through translation, and then boop, makes out new proteins. So new proteins carry out the function that is signaled by the hormone in the first place, whatever needs to get done. This is stuff like insulin creation. So like you just ate a big cake, your body goes, oh God, she just ate a big cake again. Because, don't leave chocolate cake where I can find it. I'm just saying, you know how it is. And so your body, releases hormones like ghrelin to let you know that, oh God, we've got to make insulin because we've got to digest that. We've got to break down all that sugar that's floating around in my blood now. And that's basically what's going on. Makes a whole bunch of insulin, it goes out, and we break down the sugar in my blood so I don't die of overly getting too much sugar in my blood. And that does bring us into, wait, is that how diabetes kind of works? Yeah, we'll get there in a minute. But yeah, diabetics usually either can't make insulin or make so little it doesn't really do anything. So, and we'll get into that. And some of you may know that better than I do, because you may know somebody who is diabetic in your family, or you might be diabetic, and so you might be the one to teach that to me. Because I always learn something interesting from my students. I always find as a teacher, it is my job to teach, yes, but it is also a give and take to education that I love. Because sometimes somebody can tell me something and I'm just like, I did not know that. And then I add it to my repertoire. So I always learn something from my students, and I love that. That's what I love about education. Anyway, so steroid, again, just what I said, it passes through, it finds a receptor, it goes in, it tells the DNA, hey, we need this made, goes through transcription, pops out, goes through translation, makes proteins. So that's basically a steroid hormone action going on, because steroid hormones can pass right through the plasma membrane because they are both lipids. Clever. And lipids don't dissolve in the liquids that make up your circulatory system. So it's a great long-distance calling device. Now, non-steroid hormones. Now, this actually has more to do with diabetes. I did that because it just popped into my mind. But this actually is how we control blood sugars, the non-steroid hormones. It's also where we get fight or flight. Like, when you get scared and you're watching something and then all of a sudden you hear a bang in the kitchen and you're like, and it was the cat. I have 3 cats, so yeah. You make me going, well, what do the cats think about Monty? Unfortunately, they don't think too highly of Monty. I actually have a pretty, I'll if I can find it, I have a pretty funny picture of one of my cats looking at Monty, and it's just like, I'll pop that in here. It's kind of funny. So anyway, but yeah, poor Monty. He don't get no respect from the kitties. One of them just keeps slapping him in the head, and Monty just curls into a ball and cries. So, anyway. So, cell membrane permeability, this is like, are we going to let things through? Are we not going to let things through? It includes amines, peptides, proteins, and glycoproteins. So, unlike the other one, where basically says, yeah, come on in, this one we need a receptor protein on the outside. This is the one that it can't get through the cell membrane unassisted. So, we need a receptor protein. So, the receptor protein comes in, non-steroid hormone comes in, binds with the receptor protein, and then it undergoes basically it goes through and it forms into a second messenger. It activates the enzyme, energy gets added to it, and it usually gets turned into a second messenger with cyclic AMP. And then it goes down to the cellular functions, such as breakdown of glycogen or something like that. So this guy, what he basically needs is he needs somebody to meet him at the cell membrane to let him in to start a whole cascade of steps to go ahead and then go through the change inside the cell to produce something, to make something, or something like that, or for the cell to go, oh, okay, I can go ahead and split the two and go through mitosis. Right on, my friend. So this one needs a receptor protein on the surface, whereas the steroid hormone doesn't. He can just go right on through to find the receptor inside the cell. So non-steroid receptor outside or on the cell surface, steroid receptor in the cell. So that's one way to keep them straight. So again, hormone binds to the outside, acts as first messenger. Result is either an increase or decrease in some of the second messenger. Second messenger activates this protein cascade where basically a whole bunch of enzymes go, whoa, 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 in a group. And then a G protein regulated using cyclic AMP as the second messenger, because he gets turned on and he goes, oh, okay. And he goes down and tells whatever cell function needs to be turned on or off. So hopefully now you've got the difference between steroid, receptor in the cell, non-steroid, receptor on the surface of the cell. All right, now remember those weirdos I said were steroid-like? Well, here they are. They're called prostaglandins, also known as local hormones. These guys are locally acting. We need them in really tiny amounts, and they disappear really quick. They're like that. That's why they're local. They don't need to be traveling long distance through the body, especially any of the paracrine hormones that are coming out. Not stored. Usually they're produced just prior to release because they have a really short life. So they just go, what? Ah. And they have a variety of effects. And sometimes they usually work in conjunction with other hormones to alter the message of that first hormone. So, the hormone's saying, do X, do X, do X. The prostaglandin will come and attach, and it says, instead of do X, it's like do X, but also Y. So it will sometimes alter the message of the first hormone to get what we want in the signal transmission. So these guys show up like boop. Now, half-life. So, and I'm not talking about the video game. Again, nerd. So anyway, half-life is basically the time it takes for half of the hormone to be removed from the plasma. A short half-life means a quick turnaround, and a long half-life means longer-lasting effects. So, and some of the hormones we're going to be talking about and what they're going to be doing, like for instance, amines, they have a half-life of about 2 to 3 minutes. It's interesting, the hormones that come out of your thyroid, which are T4 and T3, they have drastically different half-lives. So T4 hangs around for like 7 days. T3 is only for like 0.75 of a day. So, 2/3 of a day. So, wow, okay. Polypeptides, anywhere from 4 to 40 minutes. Proteins, anywhere from 15 to 170 minutes. And steroids, anywhere from 4 to 120 minutes. So, it's really different depending on what they're signaling for. And we're going to go over a lot of these, and what they do and what roles they play in your body. So don't panic and go, oh, fear not. We're getting to it. So anyway, generally, how do we control these guys? Because they're so potent, and we've got upregulation and downregulation, if it's too quiet or too loud. How do we control these guys? So there's anyway of 3 types of control. So usually hormonal control of tropic hormones is by the hypothalamus. He's our guy in control. He's the one that's pretty much running our endocrine system from the central nervous system input. So sometimes the central nervous system goes down to the hypothalamus and says, hey, how about you do, we need this, 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 or oh my God, zombies, panic. Right, Monty? Yes. He's like, what's a zombie? Exactly. So, Now, the hypothalamus then tells the pituitary to do something, and then usually the pituitary then cascades hormones down to any target gland there happens to be, and those target glands usually talk to the cells, under their purview. So we got nervous control by the autonomic nervous system. This is where we get the fight or flight or the rest or digest. And then we've got hormonal control by regulating blood levels. And again, this is usually the pituitary that comes back and goes, oh. So what's happening here is we have a whole bunch of interesting feedback systems going on. So hypothalamus, sometimes the central nervous system tells the hypothalamus to release, which tells the pituitary to release. And sometimes you get a regulation feedback right there that says, oh, okay, so I put it out, so now I stop. Or it goes down to the target glands. Or sometimes the pituitary goes up, talks to the hypothalamus, which again, then he goes directly to the target gland. It's a fun thing. So yeah, we've got hormonal control by hypothalamus, nervous control by the autonomic nervous system, which gives you the fight or flight stuff, and the hormonal control by regulating our blood levels. And usually, one of them is always constantly monitoring the blood. So first, hypothalamus secretes releasing hormones that target the anterior pituitary gland, which in turn secretes hormones. So again, here's the three mechanisms right here. So our friend, the capillary blood going through the thyroid, and he sits there and is a whole bunch of monitors on the thyroid gland. And then we've got at the back, we've got 4 parts that are called the parathyroid glands. And don't worry, we'll get into each one of these and what they do and how they look. I'm just kind of going over the big things at the moment. So for instance, if, say, you don't have a lot of calcium flowing around in your blood, well, guess that goes through your thyroid, and your parathyroid glands pick that up and go, oh, we're running low on calcium. We should probably do something about that. So he secretes parathyroid hormone, which goes, hey, bones, release more calcium, for we don't have enough calcium on our blood for our muscles to work. And the bones go, gotcha, and releases more calcium from your bones. Another one, for instance, preganglionic, fibers stimulates the adrenal medullary cells. So again, you go into fight or flight, and you go, oh, zombies. And so what's happening is it goes to, like, for instance, this is just an example of one piece. It goes from your spinal cord, and it stimulates the medulla adrenal gland on top of your kidneys, and basically tells to secrete epinephrine and norepinephrine. In other words, adrenaline. So all of a sudden you start pumping out adrenaline, so that way you can run away from the zombies, because, nobody likes zombies. Anyway, we like watching zombies. I don't think any of us would like to meet a zombie. That would be not so cool. But, Monty, you wouldn't want to meet a zombie, right? Yeah, he doesn't even know what a zombie is. Anyway, so then the hypothalamus secretes. So again, another way to do this is the hypothalamus. So he gets, stimulated by the central nervous system, and he goes, hey, release hormones. And those go down to the thyroid, the adrenal cortex, and sometimes your gonads, whether you be male or female. And again, they secrete hormones. So that's the 3 releasing mechanisms we have in our body for releasing hormones upon our system. So we know what's going on depending on what's happening. So again, I love using Crash Course. I would highly recommend, after my lecture on this bit, you go watch the Endocrine System Part 1. It's a good helpmeet. And again, he has the money to get things animated that I wish I had an animation team to get. So again, like I said in my introductory video, I feel an animation is worth a million gajillion words. If a picture's worth 1,000, then yeah, an animation's worth even more, especially in anatomy and physiology, because he can show you things that I don't have an animation team to show you. So please, 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 definitely go watch the Endocrine System Part 1. And that's it for the Endocrine System Part 1. And I'll see you in just a moment for the Endocrine System Part 2, where we finish up Chapter 13. Thank you so much for watching. I'll see you in a bit.